Hello, hello, I'm Mrs. Edwards, and today we're going to be learning how to find and justify local mins and maxes using the first and second derivative tests. Then we're going to also know the intervals where the function is increasing, decreasing, identify any points of inflection, and we'll also know the intervals where our function is concave up and concave down. Ultimately, we are going to use this function to illustrate how to find each one of those. But before I do that, I want to just go ahead and outline the two major tests. The first derivative test and the second derivative test are both used to find and justify local minimums and maximums. And when it comes to these two tests, the first step is the same. So what you want to do, regardless of if you're using the first or second derivative test, you've got to first find any first derivative critical values. Those are those numbers that make the first derivative equal 0 or undefined. The reason why we find those first derivative critical values is first derivative critical values are possible or potential local minimums and maximums. Now, after we've found those first derivative critical values, what we do with the critical values changes based on which test we end up using. So let's start with the first derivative test. What you're going to do with those first derivative critical values, again, those are the numbers that make the first derivative equal 0 or undefined. You're going to put them on a number line to create a sign chart. Then you substitute numbers around those first derivative critical values, and depending on the answer, we can determine if we have a local minimum or a local maximum. There are a limited number of things that can happen. So let's say you've made the sign chart and you see that the sign changes from negative to positive. Keep in mind that when you substitute a number into the first derivative, what that's telling you is the original function going uphill or downhill. The slope of the tangent to a function that's going uphill is positive, and the slope of the tangent to a function that's going downhill is negative. So if we find out that we were going from downhill to uphill, kind of picture that, right? Downhill to uphill, we must have had a minimum. Now, if the sign chart changes from positive to negative, then that means we went from uphill to downhill, so we would have a local maximum. The best part about the first derivative test is it always works. All right, now the second derivative test, again, we started off the exact same way, finding those first derivative critical values, those x values that make the first derivative equal 0 or undefined. And then instead of making a sign chart out of those first derivative critical values, we simply substitute those first derivative critical values into the second derivative equation. Now, when you do that, keep in mind, once again, that when you substitute a number into the second derivative, if you get a positive answer, it means that you are on a section that is concave up. If you substitute a number into the second derivative and get a negative answer, that means you are concave down. So if you are working with x values that might be mins or maxes, if that possible min or a max shows up on a concave up piece, well, then it must have been a minimum. But if that possible min or a max shows up on a concave down piece, well, then it must have been a max. So to summarize that, when you substitute that first derivative critical value into f double prime and you get out a positive, you have a minimum. Students often don't like that at first glance. They think you have a positive and it's a minimum. So let's look at a picture. If we draw a parabola that is concave up, think of it as cup up. If we have a positive second derivative answer, we're on a concave up, so we have a local minimum. Now, opposite of that, if f double prime has an answer that is negative, then that first derivative critical value ends up being a maximum. Because if the answer to second derivative is negative, then our original function is concave down. If we have concave down, then the point that would be on that would be a maximum. All right, so it's kind of like cup up, frown down. Little Dr. Seuss for you. Well, as I said, the first derivative test always works, but the second derivative test, if we substitute one of those first derivative critical values into the second derivative, and we get an answer of 0 or undefined, well then, the test is inconclusive. You might think, oh, that means it's not a local min or a max, and that is not true. It is often true, but it is definitely not a guarantee. So what ends up happening, you do that work of substituting in those first derivative critical values into the second derivative, and you end up getting out an answer of 0 or undefined. Well, then you have to scrap the second derivative test and go back and actually do the first derivative test. The first derivative test is slower in general, and the second derivative test is faster. It's a shortcut, but a shortcut, like most shortcuts, it doesn't always work. So then you have to return to that first derivative test. You may wish to come back to this page because it's an outline of how you perform each one of these tests, but please keep in mind both the first and second derivative tests are used to find and justify local mins and maxes. But for now, let's go ahead and put these two tests in action using this function f of x. Okay, step one, no matter what, we might as well just go through and find the first derivative and the second derivative right up front because we're going to need those equations eventually. Okay, so now let's perform the first and second derivative test side by side. Regardless of which test you use, step one is the same. We want to find the first derivative critical values, which are our potential local mins and maxes. So first derivative critical values, those are the x's that make the first derivative, in this case 4x cubed minus 12x squared, equals 0 or undefined. Now, 4x cubed minus 12x squared, there is not an x value out there that is going to make that undefined, right? We're not going to be dividing by 0. We're not going to be taking the even root of a negative number. Okay, we don't have any domain issues. So there will not be an x value that makes the first derivative undefined. But I'm putting that on there because every time you want to think about if there is an x value that makes it undefined, if you had a fraction, you would just set the denominator equal to 0 to find the x value that made the function undefined. But in this case, we just have a polynomial, so let's focus on setting this equal to 0. I'm going to factor it, so I factored out a 4x squared to start solving. Then if I set 4x squared equal to 0, solve, divide by 4 square root, we're going to get 0. Set x minus 3 equals 0, and we're going to get 3. So it turns out the numbers that make the first derivative equal to 0 are 0 and 3, and there are not any numbers that make the first derivative undefined. Our critical values, first derivative critical values, are 0 and 3. Now this is where the two tests diverge. Let's start off with the first derivative test, but keep in mind the difference is in the first derivative test, what you're going to do with those first derivative critical values is make a sign chart. But if you are going to perform this second derivative test, you're substituting those same first derivative critical values into y double prime. Okay, so again, starting with the first derivative test, let's make a sign chart. So notice I just drew a number line, put the critical values on there, 0 and 3. We want to test around those numbers. So to the left of 0, in between 0 and 3, and to the right of 3. I'm going to check the number -1 because it's to the left of 0. Substituting -1 back into the first derivative, I end up getting a negative answer. Then I selected 1 because it's between 0 and 3. Substituting 1 back into that first derivative, I end up getting a negative answer. And then I picked a number to the right of 3, which was 4. I substitute 4 back into the first derivative and I get out a positive answer. So now to interpret that sign chart, there is a local minimum at x equals 3. Now on the AP exam, you want to say because f prime changed from negative to positive at x equals 3. So that is your official, statement. You don't want to just have the sign chart there and say, therefore, there's a local minimum at x equals 3. Okay, so specifically say, don't say it changed. You need to say f prime changed from negative to positive. Now the reason, remember that substituting a number into the first derivative, it's telling you the slope of the tangent at that x value, but more importantly, if the slope of the tangent is negative, the original function is going downhill. We call that decreasing. So our function was going downhill, it was decreasing, and then by the time we got to x equals 0, the slope of the tangent was 0 for just a second. So it was going downhill and then it tapered off for just a moment. And then between 0 and 3, it's still going downhill. So it went downhill, tapered off, downhill, and then after 3, the function starts going uphill. So downhill, downhill, decreasing, decreasing to increasing. Now in this particular example, we don't see a local maximum. But using this same test, if this would have been a plus and then that's a minus, then we would have said we have a local maximum because we would have went from uphill to downhill. Okay, how about the second derivative test? Instead of making a sign chart with those first derivative critical values that are possible mins and maxes, we're going to simply substitute those numbers into the second derivative. Now, when you plug a number into the second derivative, it tells you the concavity. If you get a positive answer, you're on a concave up, and if you get a negative answer, you're on a concave down. So starting here, if I substitute 3 into the second derivative, I get out a positive answer. So this possible local min or a max, x equals 3, showed up on a concave up piece. If it's on a concave up piece, cup up, then we must have a local minimum. All right, so local minimum at x equals 3 because f double prime evaluated at 3 is positive. All right, then how about this one, f double prime of 0? If I substitute 0 into the second derivative, I end up getting 0. Darn it. Remember, if you substitute a number into the second derivative, you get positive, you're concave up. You get negative, you're concave down, and then it would have been a max. When you substitute a number into the second derivative and get 0 or undefined, the test is inconclusive. That does not mean there's not a local min or a max there. It just means that we don't know. So we have to return to the first derivative test. So if I went back to the first derivative test, I can tell, it was redundant since we did them side by side, that the sign did not change at 0, so it is not a local min or a local max. I want to just elaborate a tiny bit more about the turtle and the hare here. The reason why the first derivative test is considered slow is because you have to take those first derivative critical values and put them on a sign chart, and when you go to substitute a number into f prime, you're going to have to substitute more numbers because you're doing the numbers around the critical values. And not only that, normally, as you take a derivative, the degree is going down. So in general, the equation you're working with is not as complicated. So substituting numbers into a second derivative equation algebraically is usually a little bit easier, which is another reason why the second derivative test can be considered a little faster. Okay, but either way, first derivative test always works, and second derivative test is a little faster but does not always work. As you see right here, it was inconclusive. Next, we're going to use the test that determines points of inflection. The definition of a point of inflection is where your graph changes from concave up to concave down, or vice versa. Okay, so if it's about points of inflection or about concavity, then we're dealing with the second derivative. Now, there is no name for this test, so I like to call this the test that shall not be named. Sorry, just a side note, I can't help myself. In Harry Potter, they spent over 500 pages to get Harry to touch the cup. I'm just saying, why not put some nachos in it and say, hey Harry, you want a chip? Anyhow, a little bit of a side note. But the test that shall not be named, to help you associate this particular test with what it can find, points of inflection. Another abbreviation for point of inflection, POI, think about person of interest. So the person of interest in the news, they're like, do you have a suspect? Well, we do have a person of interest, but they don't name the person. So if you are using the test that shall not be named, you are trying to find a point of interest, a point of inflection. All right, silly story, but ultimately, the first thing you want to do is find the second derivative critical values. These second derivative critical values are possible or potential points of inflection. So those are the numbers that make our second derivative equal 0 or undefined. In this case, there will not be an x value that makes 12x squared minus 24x undefined, but we're still thinking through that process. We won't be dividing by 0 or something, but we can find the x's that make 12x squared minus 24x equals 0 by factoring and then setting each piece equal to 0. So 12x equals 0 solved is 0, and x minus 2 equals 0 is 2. So we have our second derivative critical values. I know that I'm repeating myself, but it's hard to keep all of this straight. First derivative critical values are possible mins and maxes. Second derivative critical values are possible points of inflection. Okay, next what we're going to do is we're going to put these second derivative critical values on a number line. We're going to make a sign chart. Then I'm going to substitute numbers around these critical values into the second derivative. Because if the definition of a point of inflection is a point where the concavity changes, plugging numbers into the second derivative tells you about concavity. So I substituted a number to the left of 0, namely -1, into f double prime. You end up getting a positive answer. I picked 1, which is between 0 and 2, and got a negative. I picked 3 to the right of 2, and I ended up getting a positive. So what we now know is both 0 and 2, both x equals 0 and x equals 2, are points of inflection. And we know that because the sign changed, f double prime changed sign at these x's. On the AP exam, to justify a point of inflection, you want to say f double prime change sign. Now you don't have to be as specific when it comes to a point of inflection because it doesn't matter if it's positive to negative or negative to positive. So it suffices just to say it's a change of sign. Just make sure that you don't say it changes sign. For points of inflection, it's f double prime change sign. And for local mins and maxes, the justification is f single prime changed from positive to negative, uphill to downhill for a max, or f prime changed from negative to positive for a minimum. All right, so that's the test. And I will say this test often is accidentally called the second derivative test. You can kind of see why, because when you perform the first derivative test, you find the first derivative critical values, you make a sign chart, and then see if the sign changes. Here we found second derivative critical values, put them on a number line, made a sign chart, and we looked to see if the signs changed. It kind of seems like first derivative, second derivative, but overarching one more time, the first and second derivative tests, their purpose are to find and justify local mins and maxes. This test, where we find the second derivative critical values and put them on a number line, that is to find and justify points of inflection. Now, after we have created these number lines or these sign charts out of the first and second derivative critical values, we can get a bit of extra information. In this case, for the second derivative critical value sign chart, we can tell that in those intervals, our original function is concave up. Answers to second derivative tell you about concavity. So it is cup up. Our original function, f of x, that x to the fourth minus 4x cubed, that function is concave up from negative infinity to 0 and from 2 through infinity. It is concave down between 0 and 2. Concave down, so from 0 to 2. Going back really quick to the sign chart that we made for the first derivative, we can also tell where the original function is increasing or decreasing. Any place the first derivative was negative, the original function was going downhill. That's called decreasing. So from negative infinity up to 0, union 0 through 3, our original function was going downhill. It was decreasing. And the original function f is increasing where the first derivative is positive. So we are increasing from 3 through infinity. This might be overkill, but I want to go ahead and just summarize what it means when you substitute a number into f, f prime, and f double prime and look at that graphically, because I'm a very visual person and it really helps me to understand the tests rather than just completely memorize them. So if you substitute a number into the original function, you're getting the height of the point. You're plotting a point. If you substitute a number into the first derivative and you get a positive, what that's telling you is at that x value, your original function is going uphill. Your function is increasing. If you substitute a number into the first derivative and get a negative answer, that tells you that the original function is decreasing or going downhill. Now, if you substitute a number into the first derivative and get 0 or undefined, all you know is that x value you substituted in might be a local min or a max. Moving on to second derivatives, if you substitute a number into the second derivative and get a positive, that means at that x value on the f function, you are concave up. Plugging a number into the second derivative and getting a negative answer tells you at that x value that you are located on a concave down section of the original function. And then if f double prime is 0 or undefined, then that tells you that you might have a point of inflection. Let's just look at this graph of f and have us decide, is the answer to these positive, negative, 0, undefined? So if I substitute -6 into this function, okay, so I go to -6, that's just height. So it's up 1, 2, 3, 4, 5, 6. We get out +6. So that's just saying we're above the x-axis. If you substitute -6 into the first derivative, that tells us increasing, decreasing. So looking there at -6, let me just do that really quick. I think I can do it fast enough. Pen. If we go to -6, okay, then what is the slope of the tangent there? See how the slope of the tangent would be negative? Our function is going downhill. So since we are going downhill at -6, f prime is going to have a negative answer. Then f double prime of -6, that's about concavity. So when we are right here at this pink dot at x equals -6, notice we are on a concave down section. So the answer is negative. Now how about f of -1? If I go to -1, f of -1 is just a height. So I go back 1, up 1, 2, 3, 4, 5, 6. So we get 6 as an answer. So that's why we get a positive. Now f prime of -1, the slope of the tangent, it's telling us if we're increasing or decreasing. Well, first of all, notice there at x equals -1, we are not going uphill or downhill. So we're not going to get a positive or a negative. Then we could get 0 or undefined. This tangent line, when you are at a cusp, when you're at one of those sharp spots, you can't get a unique tangent line. It's going to teeter there. So the derivative at a cusp is undefined. Now f of 0, I go to 0. That just means what's the height? 1, 2. So the height at 0 is 2, so that's why f of 0 is positive. F prime, again, that's increasing, decreasing. So notice at the blue dot at x equals 0, we are going downhill. So since we're going downhill at x equals 0, f prime of 0 is a negative answer. Now f double prime of 0 answers to double prime, concavity. So notice at that blue dot x equals 0, all along here we are concave up. So at x equals 0, we are on a concave up section. So the answer to f double prime at 0 is positive. Okay, a couple more here. How about at 3? If we substitute in 3 into the function, we would go down 1, 2, 3. So we'd get out -3. So f of -3 would equal a negative answer. That just means we're below the x-axis. Now f prime of 3, that's the slope of the tangent at 3. It's increasing, decreasing. Well, at x equals 3, the slope of the tangent there is 0 because we're not going uphill and we're not going downhill. So f prime of 3 is 0. And then f double prime of 3 is concavity. So at 3, what's the concavity? Well, we are on a concave up piece. So f double prime of 3 is positive. Okay, last one, 5. if we go to x equals 5, plug 5 into the function, we're going to get a height of 1. So f of 5 equals 1, so it's positive. We're above the x-axis. F prime of 5 is increasing, decreasing, uphill, downhill. Slope of the tangent. So notice here at 5, we are going uphill. So the answer to f prime of 5 is positive. And then f double prime of 5 is concavity. But that yellow point there, that is where we switch from being concave up, and then all of a sudden we are concave down. So that ends up being a point of inflection. So we're not concave up, so it can't be a positive answer. We are not concave down, so it cannot be a negative answer. So the answer to f double prime of 5 would either equal 0 or undefined. Now I happen to know in this case it equals 0 because I started with the original function, which you do not have the equation. But f double prime in this case is 0, but you would at least know, since we're not concave up and we're not concave down, the answer would have had to be 0 or undefined.